So welcome to the main videos here for the normal distribution. With these, they'll be accompanied by how to use the calculator. So please make sure you're checking that out at various points. So we're going to talk a little bit about some characteristics of the normal distribution. We're going to use it to find probabilities. And then ultimately, we're going to do a couple of things. So number 3 is about solving some problems with some unknowns. Number 4, we'll talk about how we can approximate a binomial situation to a normal situation and why we want to do that. And then probably the most common of all is we can do some hypothesis testing. So what does it look like? It looks like a distribution such as the one on screen. So this might be if I were looking at height, for example. You'll have seen this come up in lots of places. It's called a bell curve, and it has a couple of characteristics. So one is it has some sort of central value here, where the probabilities, so this is the probability density, but for now, just think about this as probability. It shows that most people are distributed in the middle, if you like, okay? So it's most common to be in the middle, and we'll later talk about the idea then that the mean is the median is the mode. That's what we could say for a situation like this. Something else that will stand out is it seems to have some symmetry to it, okay? So if you have a continuous variable like height or time or the mass of something maybe, you'd find that many things meet this sort of distribution, and it's called a normal distribution. So here are a few different versions, and they are all normal distributions, okay? You'll see a few things. So first of all, in the top right, you will see mu. So this is the mean. And then you will see, in this case, it's squared. So this is variance. And the idea is that the shape of the curve depends on these two things. The one that has, for example, a mu value of 0 and is the narrowest, that will be this one here, because it's centered at 0 and it's quite condensed, if you like. It's sort of compressed into the middle part here. Whereas something like this one, which curve will that be? Well, it will be one that again is centered at 0, and it will be the widest one. So it's going to be this one here, isn't it? It's going to be the one that's the most spread out. Okay, that would be that one. Whereas the blue one would be this one here. Anything else? Yeah, well, this one is showing you that we can also shift the curve. So do you notice that this one here is centered at -2? So again, they're all symmetrical and they've all got this peak in the middle, which then diminishes to the left and the right. They're all normal distribution. So we're going to do a couple of questions to get us started. So we've got height again. We've moved the y-axis here to sort of go down the middle of the curve, okay? Because it's symmetrical, it makes a lot of sense to do that. So for a normal distribution to be used, what we can do is we can say, just bear with me, we can say that this is for continuous data. So if we have a continuous situation, the normal distribution is what we want. With a discrete variable, so this is when you were doing binomial, for example, everything had to add up to 1 in terms of the bars. So here, similarly, all of this that I'm shading now, all of this will add up to, well, you guessed it, 1. If we wanted to solve a problem like this, what we are asking is we're asking, what's the area, the bit that's already shaded in here, what's the area between 170 and 190? Okay, and the video about calculator use should show you how to do this. So this is your lower bound, this is your upper bound. You can't actually draw this at the moment because I haven't given you enough information. From the picture, you can surmise that mu is 180, but the problem is you don't know what the standard deviation or the variance, if you prefer to think of it, is. Finally, would we ever want to find something like this? The idea is no. And the reason for this is, imagine if this is height, 200. Well, nobody is actually 200 centimeters tall. You might think that they are, but actually, if we look at it closer, it might turn out that they are 200.1273, centimeters tall. So it becomes infinitesimally small when we focus on one value. So this would just have a probability of 0, and you can verify that yourself. If you do the lower bound of 200 and the upper bound of 200, you will see that result. So why is this important for us? It means that, for example, to go back to this one, which was in C, if we worked out this probability, and you can verify this yourself on your calculator, you should find that it gives you exactly the same probability as, say, that, and it should give you the same as that, okay? So although we had to be quite careful about our inequalities with the binomial distribution, we don't have to do that for normal. Some other characteristics. Yeah, so we know that mu is the center of it. If we go up by 1 standard deviation or we go down by 1 standard deviation, we will find that there are points of inflection. So points of inflection, you may know from year 2 differentiation. This is where we change from being concave to convex or vice versa, okay? So this is when your second derivative has a change of sign. It doesn't have to be a stationary point. It just sort of helps you describe and understand the shape of what's there. In practice, we don't tend to use it a massive amount in the course, but it's another property to be aware of. Also, since this is a really common distribution, we know lots of facts about this. So we can say, for example, that the inner sort of 1 standard deviation away from the mean either side adds up to 68% of the data. So what that means is lots and lots and lots of data is within 1 standard deviation. If you do 2, so if we do something like that, it rises to 95%. And finally, if we do 3, we find it rises all the way up to approximately 99.7%. So what's interesting is you don't need that many standard deviations from the mean in a normal distribution to cover the vast majority of the data. And there's this fact sort of here, okay? So if you think about somewhere like CERN, they might look at 5 standard deviations from the mean, but that really is only 1 in every 1.7 million values. So it's exceptionally rare. So if somebody's walking around, for example, saying that, I don't know, that they have an IQ, let's say, of 200 or something, well, if we say that the mean is 100 and the standard deviation is 15, that would be 100, 115, 130, 145. This would really be pretty hard to believe, okay? So the vast majority of data is within a couple of standard deviations. We're going to do some quick examples. So the idea is that when we're asked to work something out, we want to do a quick sketch to help us. So in these very quick examples, it's the diameter of something. So notice that that's a length. That's a continuous measurement. X is distributed normally with a mean of 8 and a standard deviation of 0.2. 0.2 squared is the variance. So what would be the probability of 8 or more? Well, because 8 is the middle, 8 or more would be 50% of the data. We can do something similar here. If this is 8, 7.8 is below, 8.2 is above by the same amount. And we notice that that seems to be the same as that 0.2. So this then must be my 68% that we saw on the previous slide. Okay, so knowing the properties allows us to quickly work out some probabilities. You can use your calculator to work this out, and I think it comes out 68.3%. So we can also use our calculator for a lot of questions in this chapter. So Pause and have a quick go at the question on the board using your knowledge of the properties of the distribution. Okay, and here this is 2 standard deviations. So this should have been 95% for the top one, and 115, so we want to draw this one. So this is 100. 15 is there, isn't it? So the best thing to do is going to be to say something like this. Between 85 and 115 is 68% of the data. So what's left over? Well, it's 100% minus 68%, which is 32%. And then because it's symmetrical, that needs to be broken up evenly for these 2 parts. So we're going to say 16%, 16% here. And that's our answer, okay? This is approximately 16%. So we're going to go on to some harder questions. I leave this one here because this is, again, just testing to use the calculator, and we'll cover that in that video. This one, slightly more difficult question. So it says the criteria for joining Mensa is an IQ of at least 131. Assuming that this is the distribution, it's a good idea to write this down. This often will give you a mark. Not here, but in other ones where you use the wording, it can sometimes give you a mark. So determine the percentage that are eligible. Okay, so this is just going to be my lower bound as 131. What to put for your upper or your upper bound? Well, it goes on forever, but we've seen that it goes down very, very sharply. So we should do something like this, 131, and your value here, if you put 1,000 or something like that, that should be very, very safe. I'd encourage you here to try 1,000, try 1,000,000, and compare your answers, and you should see practically no change. Okay, so we're going to do this. Our mu is 100, and our standard deviation is 15. So let me just find the question. Where's the Mensa question? Okay, so my answer for this is going to become 0.01938. You can write more decimal places. You need really at least 4 is a good idea, okay? But just write more. You won't get marked down for writing more, but you can lose marks for writing less. So the probability of joining Mensa is equal to 0.01938. You will see why I've written it like this in just a moment. So that's my answer to part A. Part B. If 30 adults are randomly chosen, 30 is a whole number, isn't it? This is a whole number situation, the number of people. The probability that at least 3 will be eligible to join Mensa. So what's this about? Well, what it's doing is it's recycling a probability from before with a binomial, because let's talk about the distribution of people who can join Mensa. I'm going to give it a different letter now. That will be binomially distributed. N and P are the values I need. So 30, so there's 30 people who could join. And the probability of joining Mensa is actually this number that I just found out before. So this is the correct distribution to use for part B. And then I'm trying to find out that at least 3. So this is the probability that I'm interested in. And depending on your calculator, if you have a non-graphical one, you will need to do this calculation. Or if you have a graphical calculator, you may be able to find this out straight away. This should give you a value of 0.02001. So that's my 4 significant figures. So this is quite a common type of question. In part A is an average person having an IQ. So X is really about, this is about IQ, okay? Whereas Y is about, you know, joining Mensa or eligibility to join Mensa. Okay, and the two things are related in such a way. So pretty common question, that one there for you. Right, we're going to leave that section there. So that sort of takes us up to the end of 3A and 3B.